Good. So I want to thank Emmanuel, Nadav, and the organizers of this meeting for letting me speak, even though my talk has nothing to do with quantum simulations and superconducting qubits. So I hope you will forgive me. But this is not the only apology I'm going to make. I'm going to make another apology. So I'm going to tell you about an undergraduate project at the Technion done by a student, Noam Tur. And it's going to be a very simple question that I want to address or present to you in the theory of Lindblad evolutions. Now, I'm pretty sure that this question has been asked before and has been well understood by many people. Perhaps some of them are already dead. But we could not find this question raised and answered in the form that I'll present to you. And actually, one purpose of this talk is to ask this distinguished audience, if you know who deserves credit for this question and answer, please tell me after the talk. So the student, Noam Tur, is a student of the lab of David Gershoni, and David Gershoni is happily busy building cluster states on demand. But even though one of the big contributor to cluster states is sitting in the front row, I will not talk about cluster states, but I want to talk about one elementary part that related to photon generation from quantum dots. So here is a description of the system. So there is a quantum dot shown in the middle. This is in the ellipse. And it has various states, but for the purpose of this talk, you can think that the quantum dot has just 4 discrete levels, which are labeled by 0, 1, 2, and 3. And the quantum dot can emit a light, and the light can be polarized, as shown here. If there is a transition from 3 to 1, you get vertically polarized purple photon, and if it decays from 2 to 1, you get red, horizontally purple photon. However, the system is not isolated. It is coupled to many baths. So one bath is the electron-hole bath. The electron-hole bath feeds the quantum dot with electrons and holes, and when the electrons and holes recombine, they generate these photons. It is also coupled to a phonon bath, and the main thing I'm going to talk about is the triangle shown on the right, which is called here detector. This is the photon bath. And so what is happening in reality is you measure the photon color and polarization, but you want to simulate the system, and you simulate the system by writing the Lindblad equation for the quantum dot. So far, I've lost everybody, or it's still comprehensible? Okay, some people.
Why does the V go only from 3 to 1 and not from 3 to 2?
Oh, there is also another one that goes from 3 to 2, but I didn't want to clutter the picture. It's a good reason. Okay, so the interest, the student was given the following project. You do the following thing. You look at the conditional photon detection. So there is one event where you detect one photon with a specific color and specific polarization. And when you detect this photon, you set the clock to 0. And then, conditioned on this measurement, you want to measure another photon with, say, a different color and different polarization, and you are interested in this conditional probability, P, of the second detection conditioned on the first detection. So the first detection prepares the system, prepares the quantum dot, and the second detection is a measurement. So, and the plot one gets when one does the experiment looks a little bit like the picture shown on the right. So it's a complicated picture. And the student had to reproduce this picture. This was his project. Okay, so as I said, so now there is something funny, you know, there is something funny about this question, and I want to explain what is funny about this question. When you teach students about open quantum system, the description is shown here in the lab. So if you, conceptually, the simplest thing is to look at the closed system where you let's consider the system which is the quantum dot and the photon. Then the quantum dot and the photon would evolve unitarily, and in the theory of open system, the rule of the game is that you want to study only the evolution of the quantum dot and forget the photon is considered as a bath. And the rule, when you teach an open quantum system, the rule is that you define the bath as that system which is inaccessible to measurement. And the system which is, for which you do the evolution is the system where you want to measure. So, but in this setting, it is reversed, right? On the one hand, I want to use quantum evolution for the quantum dot, but the measurement is done on the photon. So it is not according to the standard description of open quantum system. And the question then arises, how does the dot know about the measurement of the photon, which occurs in the bath? And a more practical question is, I detected the photon with a specific color. But when I do the simulation of the problem, I look at Lindblad equation for the quantum dot. What observable in the quantum dot is supposed to represent the detection of the photon? They both live in different spaces. You wish you were somewhere else now? Okay. So let's start. How am I doing with time?
You spent only 6-7 minutes of your time.
Okay, thank you. So let's start with the easy case. The easy case is to study, let's look at the unitary evolution, and let's look at the standard rules of quantum mechanics. This is conceptually simple, but computationally it's a nightmare. So when you learn quantum mechanics, we teach the student the following, that measurement is a preparation of the system. So a measurement does not reveal the pre-existing state of the system. It prepares the system in a new state. This is what a quantum measurement does. So Columbus didn't discover America. He created it. So, okay. Determined it, thank you. And then Born rule says, what about conditional measurement? So this is this other bracket. Born rule then says like this. If the first measurement prepares the system in the state phi prime, and the second measurement detected the system in phi, then the conditional probability of phi prime evolving to phi will be given by this expression, which is just an expression of Born rule that we see in textbooks. But if you have to remember that phi and phi prime are the states of the system after the measurement, not before. You're with me? Okay, and by the way, if you do this computation for a closed system, you always get a picture which is symmetric with respect to t going to minus t. This is time reversal. The picture I showed you before was not like this because it's an open system. Okay, now we don't want to do the unitary evolution because it's a computational disaster. The quantum dot is a finite dimensional quantum system, but all other systems in the game, the radiation, the phonon bath, and the electron hole bath, are all infinite dimensional quantum systems. So if we wanted to simulate them, we would need to simulate a huge quantum system. We don't want to do this. So we only want to simulate the quantum dot. But at the same time, we only want to make the measurement in the bath. So this is the challenge. And now, let me first use the Born rule as I did before for this Lindblad type evolution. So let's imagine that I detected the purple H photon. Now you have all the errors. Emmanuel, is this making you any happier, or you're already depressed? Okay. So suppose I first detect the purple photon, which is horizontally polarized. According to the rules of quantum mechanics, this means that I prepared the quantum dot in the state 2. You're with me? You agree? And now suppose after time t, I detected the vertical red photon. Then this would prepare the system in time at state 0. So now, if I were to use the Born rule as it is stated in books, the conditional probability for detecting the vertical photon after the horizontal photon would be given by this expression on the right, where the only modification I changed is that I replaced the unitary evolution by Lindblad evolution. This is what one would do naively if one would translate Born rule to Lindblad setting. Nobody is protesting. But if you do this, you can't reproduce the picture I showed you before. And Noam succeeded in reproducing the picture shown before if you replace the 0 by 1. So a rule that seems to work is that you do not compute the probability for preparing the state 0, but you compute the probability looking where the system came from. But we know that in quantum mechanics, a measurement doesn't tell you where you have been. It tells you where you're going. So the question I wanted to raise is, why does this rule work? Now, I think this rule is used by almost everybody who does this Lindblad, who does detection of photons through Lindblad. And they all use this equation, and I'm sure they understand why, but I did not. And I wanted to understand why this rule is a good rule. Okay, so another way of formulating the rule is like this. I want to ask, what is the correct dictionary that tells you how to translate a measurement of a photon to a measurement to an observable of the quantum dot? So, if I accept that the first measurement of the first photon, phi prime, determined the state of the quantum dot at the state psi prime, then the quantum dot evolved by some Lindblad equation. And then I ask the question, what is the quantum observable, E phi, in the quantum dot, which represents the detection of this second photon? So the question is, how do you find this observable? What is its meaning? And how to reproduce this curve that is shown on the right? Okay. So let me jump to the answer. So the answer turns out that the observable of the quantum dot, which represents the detection of the second photon, is not the final state of the quantum dot, but it is the filling rate of the final state of the quantum dot. So first, let me say something about rates in Lindblad equation. So Schrödinger's, I want to distinguish two pictures. One is the Schrödinger picture, and the one is the Heisenberg picture. So the Schrödinger picture tells you that the quantum state rho evolves linearly with a Lindbladian L of rho, where the Lindbladian L of rho has two pieces. One, the first piece, the commutator of H with rho, is the unitary standard unitary evolution. And the additional terms represent the fact that the system is open, and the operators D of alpha are called jump operators. Now, there is a picture which is the Heisenberg picture, which is the dual of Schrödinger picture, where instead of looking at the evolution of the state, you look at the evolution of observable. So the observables similarly satisfy a similar linear equation. dA by dt is L star of A, where L star of A is again made of two pieces. The first one is the Hamiltonian piece, it's a commutator. And the second one is this jump operator piece. Now the two operators, L and L star, are related by duality. So duality, for example, flips the sign of the unitary evolution, and it puts into D a star, which I'm not describing how this star is, how to compute this star, but there is a star. And the relation between the Schrödinger and the Heisenberg evolution is written in this equation, that trace of A rho dot by Schrödinger equation is the same as trace of A of L of rho, but by definition of what is L star, this is the same as trace of L star of A of rho, but then by Heisenberg equation, this is the same as trace of dA by dt of rho. So Heisenberg equations allow me to determine operators that are rates, dA by dt. So let's consider an example of what do I mean by, let's consider it concretely. In this case, let's consider a decay of a two-level system. The two-level system has an excited level J, which decays to a ground state K, and it emits a photon which I'll call JK. So now, by the photon current, the rate of emission of photons from J to K is the rate of filling of the ground state, right? The rate at which the ground state collects events is the rate at which photons are emitted. Now, the observable associated with the rate of growth of the ground state is a rate thing, and then it is given by this equation. It's L star of KK. So it has something to do with the final state, but it is not the final state. It's the rate of the final state. You're with me? It's too much of a detail. You don't care. Anyway, so what is the rate of KK? It turns out to be just the action of the adjoint jump operator on KK. And this turns out to be up to a constant JJ. So the Born rule takes a slightly different form in the sense that the Born rule for the photocurrent is given by trace of d star of KK e to the TL rho, when rho is the initial state of the system. So Born rule gets modified by the fact that you don't plug in the state of the system after the measurement, but the state of the rate of the system after the measurement. That sounds like a little detail. So what does it mean in the concrete context that I've been describing? Suppose, for example, I'm interested in the conditional probability of detecting at time t equals 0 a horizontally polarized violet photon, and then at time t, detecting a vertically polarized, say, red photon. Then according to the equation I showed you before, it is given by trace of d star. The first, the violet photon prepared, the horizontally violet photon you see here, it prepares dot in the state 2,2. Then the state 2,2 is going to evolve by Lindblad evolution, and then we're going to measure the vertically polarized red photon. But what we are measuring is the rate of the rate at which the rate of feeding or the rate of growth of the ground state, which is D00, which is 0, 0, and the rate is D star of Z0, 0, but D star of 0, 0 is gamma, replace gamma and then replace it by 1. So this explained to me the puzzle, why what Mr. Noam Tur did gave an answer that agreed with the experiment, and how does it fit with the Born room. And as I reached the end of my talk, and if someone among you knows who asked this question and answered it, perhaps Archimedes, I don't know, tell me. Thank you.